Okay, in this video we are going to prove another property of cut edge in a connector graph. The statement reads as follows. Okay, let E be a cut edge in a connector graph, then the number of connected components in G minus E is equal to 2. Okay, so before proving, let's look at an example. So let's consider this graph G. So if you look into this particular graph, we can see that okay, this DF is a cut edge. And similarly Gi is also a cut edge and Ij is also a cut edge. So here we have the graph obtained after deleting this edge df. So here we can see that if you look into this graph G minus df, okay, we have two connected components here. Okay, so that says we started with a connected graph, and here we can see that the number of connected components in G minus df is equal to 2, exactly 2. Similarly, you can see that if you delete this particular edge, okay, we have this connected component and this connected component. Again, the number of connected components is 2. Similarly, you can also see that this is also a cut edge. If you remove that, okay, again we have this connected graph and this isolated one, okay, a connected graph. So in that case also we can see that the number of connected components is 2. Okay, so it seems like the statement is true. Okay, so let's go and prove this statement. Okay, okay, so let E equal to UB be a cut edge, okay, in graph G. Okay, let E UV be a cut edge in G. Okay, so cut edge by definition it means if you remove this particular edge, then the graph will become disconnected. Okay, and one endpoint of this edge will go to one connected component and another endpoint will go to a different connected component. Okay, so that says U and V will go to different connected components. Okay, so that says the number of connected components is greater than or equal to 2. Okay, so if you remove this particular edge, since that is a cut edge, then you must go to one component and we must go to another component. So we have number of connected component at least 2. Okay, so since E is a cut edge, U and V are in different connected components in G minus E. Okay, so that says we have at least 2 connected components. Okay, therefore the number of connected components in G minus E is at least 2. But here we have to prove that that is exactly equal to 2. Okay, and that's what we are going to show. Okay, okay, so let's use a new page for that purpose. So here you know a number of connected components in G minus E is at least 2. Okay, so let's look at this graph G minus E. Okay, and suppose that this is the vertex U and this is V, UV, and we deleted this edge. Okay, so next what we are going to do is we are going to consider a vertex W, okay, which belongs to our original graph. So this W is an arbitrary vertex, and if you are able to show that this W it belongs to either this U or this V, okay, then that says the number of connected components is exactly 2. Okay, and that's what we are going to do next. Okay, so let W is a vertex in our original graph G. Okay, and since G is connected, okay, there is a path between this W and V. Okay, either using this edge or without using that edge. Okay, let's see what is going to happen. So okay, So if there's a path from W to V without using this edge, okay, that says, okay, in one component of G minus E, okay, W is, okay, in that particular component W and V are adjacent, not adjacent, they are connected, okay, and W belongs to the connected component in which V contains. Okay, if that is not the case, then okay, the path contains this E. Okay, so there will be a path from W to U, and from using this edge we move to V. So that says in the, okay, that this W will be in the other component, okay, where this vertex U contains. So that says this W will be okay, reachable to either V or U. Okay, thus this is true for any other vertex. Okay, this W is reachable to V or U in G minus E. Okay, so that says this W cannot be isolated from this U or V. Okay, so it must be connected to V or connected to U in G minus V. Okay, so that says the number of connected components is exactly 2. Okay, get W. Okay, so let me complete the proof here. Okay, since D is connected, okay, there exists a path P, okay, from say W, okay, so from W to V. Okay, so there exists a path from W to V, okay, using some path of certain length. Okay, we don't know anything about the length. Okay, so that is not required here. Okay, in our original graph G. Okay, so if this P, if P does not use the edge E, okay, then we can see that then P, okay, if it does not use this thing, okay, then we have this path P, then P, okay, it is going to be a path from this vertex W to V in our graph G minus E. Okay, so that is one case. So if this is not the case, if this P does use this edge, first it will go to V, then using this edge it will move to V, because we are talking about a path. Okay, so in that case we can see that this W will be connected to U, okay, using that part of this path P. Okay, so here if P does not use, okay, so if that path uses the edge G, okay, then okay, P will be of this form, right? Okay, you will go from W to U, okay, through some path, okay, through some path, something like this, okay, then use this edge to go to V, okay, then use that edge to go to V. Okay, so we can see that, okay, since we are deleting this particular edge, and if you look at G minus E, we can see that there will be a path from W to U. Okay, so that says this W, it will be connected to either V or U, okay, in G minus E, and it is not connected to both U and V in G minus E. Okay, okay, so that is not possible because here this E is a cut edge, right? So if we use the edge G, then okay, the path which looks something like this, right? And that says, So we are deleting this edge, so there is a path from this W to U in G minus C. Okay, so that W is connected to either U or V in G minus C. Okay, and that says the number of connected components is exactly 2, so it cannot be less than 1. Okay, from the previous thing we have greater than or equal to 2, and that says that is exactly equal to 2. Okay, so that says the number of connected components in G minus C is exactly 2, and so that's the proof. Okay, so we will see some more properties in the next few videos.